think you probably all know what fast tool servo turning is. Nevertheless, I will give a short introduction of what the intentions are and then show you some of the aspects that we considered in ProSurf and also some of the developments that we have made within the project. So basically just to get one step back, when we have a structured surface that we want to replicate on a technical part, there are many applications for structured surfaces that you can find in nature or in technical applications. Basically, all these applications consist of some kind of a free-form shape that you have as a base substrate, and you've got a structured surface geometry that you want to apply on this free form. And that is actually the challenge in machining when making molds for this, when replicating this, and so on. And we have chosen fast tool or tool servo turning in this case as one of the manufacturing methods. And there are a couple of reasons for choosing fast tool or slow tool servo turning. So first of all, you have this freeform base shape of the substrate, so you cannot directly turn it on the center of your lathe. This is simply not possible. You could use these features and raster mill them, very tiny features. However, that would take extremely long time if it is at all possible to do this. You could, of course, use other processes like laser processing or so on, but usually these include or exclude applications where we need optical surface finish in this case, because laser processing always yields insufficient surface quality for this. A thing that would be usable is a process like photolithography, but this is very expensive to make the molds, and it's also limited in terms of dimensional features or dimensional complexity. So what we basically do is with fast tool or slow tool servo turning, we have a dynamic axis that we add to a turning setup. And in this configuration, we are able to machine surfaces with a non-rotational symmetric shape. Usually, fast tool servo is an add-on component to a normal lathe or ultra precision machine. It is usually mounted on the Z-axis. It can be used in this configuration, or it can also be mounted on a B-axis table that you have additional degrees of freedom, which in this case is required to do true freeform shapes as a base geometry, and then have the fast tool servo just be used for adding the geometric features or the microstructure or nanostructure on top of this. There are different kinds of fast tool servos. Most fast tool servos are referenced to the linear axis, to the x-linear axis and turning direction, and to the C angle or the angle of the spindle used for turning, so that you have a reference of the exact point on your workpiece that you want to machine, and can determine the actual height that you need in this case. And you can use these fast tool servo systems in an open or a closed loop control. Most fast tool servos are used in a closed loop control to get the maximum precision. However, as for Nanofesto servo turning, that I will show you later on, we're using actually an open loop controlled system. So there's basically no feedback of the tool position, just an open loop control of the height that we want to machine. So when wanting to machine microstructures or nanostructures, using this type of technology, a lot of emphasis is put on the tools that we apply for the diamond machining. So for microstructures or even nanostructures, the tools are typically of a quite fragile geometry. We have got something like sharp pinpointed tools, or we have cutting wedges with a very small nose width that basically determines the structural extent of the structure in feet direction of the turning motion. You can see here on the top right side a very small tool with a width of only 12 micrometer. And this is, for example, used for machining diffractive features on an optical surface with the Fast Tool Servo. You see that these tools are quite delicate, and as you might imagine, they need to be handled with a lot of care. There are some possibilities to extend the robustness of these tools by using, for example, edge preparation techniques, where we deliberately round off the cutting edge of this tool and actually can prolong the tool life with this, because the rounded cutting edge is not that much affected by chipping and so on. And one thing that within ProSurf that we considered a lot is using complex shaping techniques for generating these fine geometric features on the diamond tools, which is in this case done with a combination of laser machining. So laser machining the rough shape of the diamond tool, and then using fit milling to generate very tiny features like these small cutting edges on the tools. And then we can generate these highly precise tools with small extent and use them for microstructuring applications. As you might imagine, these very small tools need to be set up in a very controlled fashion on the machine tool, especially if we add the B-axis for angular alignment of the tool. So we have to put a lot of effort into correctly aligning this tooltip to the center, or at least knowing the position of the tooltip, or aligning it to the rotational center of the B table, so that we are able to precisely set the angular position of the tool without affecting its infeed or lateral position in this case. You can do that in basically two different types of compensation. You can do a virtual offset compensation, where you just determine the offset of the tool with respect to the rotational center of the B-axis, and do all the compensations in a programmatic fashion, so that you are establishing a virtual rotational axis at the tooltip that you want to have as your main pivoting point. And of course, you can also just align the tool to the center of the B-axis. Usually in this project, we used a combination of both of these approaches. First, we manually aligned the tools close to the center of the B-axis, and then just compensated the remainder, the remaining difference, using offset compensation techniques and establishing a virtual center. You can see how this setup procedure looks like. Usually the CCD camera is used just looking at the tool and having the center somehow in the image, and then aligning it manually, and then doing some test cut in order to determine the correct position within the turning setup. Nevertheless, when you machine quite complex substrates, freeform surfaces, you have the challenge that the loads that act on the diamond tool are very much varying with the cut. So it depends on whether you have maybe an inclined angle in feet direction to the left, to the right, or if it's rectangular engagement conditions, so to say, in the tool. So you always have to consider what kind of stress is put on the diamond tool. Do I need to worry about this when cutting? Is the load maybe too much for this very fragile cutting edge? So what we did is we first of all did some simulations in order to establish stress distributions and profiles on these cutting edges and to determine what is actually handleable by the tool, what can be handled and what not. And we developed some calculation tools where we can just determine and visualize critical tool engagement conditions and tweak the process parameters in a way that some critical conditions are not exceeded or not met during cutting. This was done on the one hand in Bremen, at Bremen University, and also the software tool, which you can see on the top right, is a development of Huddersfield University that also includes calculations on the cutting force and takes different machining paths into account and so on. So last but not least, if you've set up the tool and are ready to cut, there are a couple of performance factors that you need to consider, especially when machining very small and definite features in the machining process. Of course, you have to consider the angular synchronization of the tool, so that like in the case on the top left side, that you machine feature in the right orientation per revolution, and that you do not have any offsets that you're generating there. As you can see in this example, this works quite well because we have a straight line between these different features that we have designed. So synchronization is quite good in this case. Another determining factor for the structures that you can machine is the dynamics of the Fast Tool Servo, which basically determines the lateral extent in cutting direction that you are able to machine. And this is a combination between the amplitude and the frequency that the respective tool servo is able to achieve. And you can see some test cuts where we try to determine some performance factors for the Nanofesto servo in this case. Last but not least, you have the geometric fidelity that is of a lot of importance. Just not only the height of the structures that you machine, that you set in the Fast Tool Servo and that are transferred to the surface geometry, but also the shape that you generate using your diamond tool. And there you have to consider that the shape shall not only be achieved in the manufacturing step, but also in the replication steps afterwards. And you can see here these two graphs on the bottom right of this slide are the shape of the mold used before replicating this into a plastic part, and then having that same feature measured after replication. You can see there are a couple of artifacts that are the result of this of the molding process and the structured geometry that we wanted to achieve. So for the remainder of the presentation, let's dive into a couple of processes that we applied in ProSurf. And the first one is the Nanofesto servo turning that I've already mentioned quite some times. The important feature in this case is that we have a Fast Tool Servo that operates in a range between 0 and about 1,000 nanometers, so a very small scale of amplitude, but can change or can work at a bandwidth of 5 kilohertz, so that we have a typical turning operation with about 100 RPM and still have enough capacity for generating enough features per revolution on this turning setup. And with Nanofesto servo turning, you can generate actually about 3,000 pixels per revolution on such a workpiece. And what we use this for is for generating holographic surface structures or diffractive structures. You can see this in this case, This is just a small section of such a modulated workpiece. Basically what we do is we have a specific image that we encode into a rotational diffractive pattern, and then use the Nanofest Tool Servo to generate the respective height levels. And the rest, the tool shape is already considered in the calculation. So what is done is that we cut this kind of hologram. It's a quite fast process, takes about 20 minutes or so. And then we can use this later either as a direct metal mirror, illuminated with a laser source, and then have a image reconstructed that is actually not readable beforehand by the human eye, but simply the effect of the holographic reconstruction. And one objective in ProSurf was to establish this kind of process, this kind of features on replicated polymer parts. So using these diffractive substrates as a mold for plastic replication. Another process that we considered, especially in Hong Kong, is the virtual spindle-based tool servo turning. This is a technology that's actually not very much like the fast tool servo turning that I've shown earlier, but actually the fast motion is generated by other linear axes in this case. The general approach of this VSTS turning is that you establish a virtual rotational axis somewhere on your turning lathe and have all the axes work in cooperation with each other, so that the rotation of the main spindle and the linear axis just coincide in a way that you have a virtual turning center somewhere on your workpiece. And we use this in ProSurf to generate hydrophobic surfaces. You can see here on the top left side there the specifications. So we have different turning centers on the workpiece, and use this virtual technique to switch between the different axes, generate these kinds of features, and then have a lot of them on a surface to generate a hydrophobic surface, replicate this, and have a plastic part with a hydrophilic features that we can use for the functionality that I will show you later on in the demonstrators. This technology is actually quite powerful. It can not only be used for these, let's say, rather simple types of structures, but for almost all types of complex surfaces, even hierarchical microstructures that you can generate. So generate a larger dimension features such as a sine wave pattern or so on, and have a Siemens star structure type on top, or a micro lens or nano lens array on top. And you can do this with this VSTS turning as well. And this was also evaluated within ProSurf. Another extension of this process is the modulated diamond cutting. Instead of just moving the turning axis to a fixed position on your workpiece, in this case, some kind of a milling strategy is used. So the rotational center is constantly moved, so that you can, on any point of your workpiece, generate some kind of a milling motion with your diamond tool, and then generate channel structures, for example, with a structure on top that provides a some kind of functionality, such as hydrophobic behavior and so on. You can see here also results from ProSurf, where I see, or not only from ProSurf, these are a bit older, but you can see that there are some channel structures, and there's a microstructure or nanostructure on top that provides another functionality, and you can use this in an extended way to generate functional surfaces on almost any kind of substrate. The last point that I would like to mention is that we also used on-machine metrology for improving the accuracy of fast tool servo turning in this case. There has been a lot of work done by Huddersfield, and I think Zen will talk about this in a lot of detail in his in his talk that will come right up my talk, right up after my talk. So I will not go much into detail about this. It's simply that we that Huddersfield used in-machine metrology to map to get an error map of the surface and fed that back to the Fast Tool Servo control, and thereby was able to significantly improve the performance of the FTS machining process in this case. So there are a lot of things that we learned within ProSurf on this technology. We have developed dedicated processes for generating functional surfaces, especially on freeform geometries or substrate geometries. We've considered a lot of tool alignment for having especially Nanofesto Tool Servo turning on arbitrary freeform base shapes. We have considered the varying process loads in this case, and also looked at specifically designed diamond tools that maybe aid in generating these kinds of microstructures in a Fast Tool Servo turning process. And we considered a lot of processes like Nanofesto Servo turning, virtual spindle tool servo turning, and so on. So with this, I thank you very much for the attention, and I'm happy to answer your questions.